All right, so before we get too far, do we have any questions about 7.3 or 7.4, which is the large sample size confidence interval and the small the small sample size confidence interval and the estimating the proportion, right? Are those two sections. Second. Yeah, so these two are due tonight, 7.3 and 7.4. I noticed that on these ones, I didn't have the allow you to work after the due date setting clicked, so I changed that this morning. I don't know if you guys, if you didn't get an 80 on 7.2, it wouldn't let you go back and do it because I didn't have the setting clicked on it. But now it's all set up, so it's ready to go. Because there's a prereq on each assignment, right? So today, we're definitely going to get through 7.5, and hopefully we can get all the way through 8.1. But 8.1's pretty dense. It's the introduction to that chapter, which is actually testing the null hypothesis, which is what we've built up to throughout the whole summer. So I have the due dates set. These due dates might change a little bit. What I'd really like to do, though, is get all the way through Chapter 8 by the end of this week so that next Monday we can review for the 7 and 8 test, and then take the test next Tuesday, and then next Wednesday review for the final, and then take the final next Thursday. All right, so we only have 8 more class periods left. Summer flew by pretty quickly, all right? So, or maybe it didn't, who knows? To me it did, it seemed that way. All right, so we're going to start on 7.5 today. So 7.2 dealt with estimating the confidence interval using a large sample size, right? Creating a confidence interval from a large sample size. 7.3 was creating a confidence interval from a small sample size, right? Estimating the mean. 7.4 was estimating the proportion, and it had to have a sample size that was large, right? Over 30. And then 7.5 actually deals with how big should our sample size be if we want to be X confident, right? So if we want to have 99% confidence, how big does our sample need to be? So it's kind of the opposite, right? It's working the opposite direction of the previous 3 sections. The other one said, well, based on this sample size, create a confidence interval. What we're going to do in 7.5 is, well, if I want to be this confident, or if I want a certain confidence interval, how big does my sample size need to be? All right, so we're going to be finding n in 7.5. Okay. So determining the sample size. And then we don't deal with 7.6, that's estimating the variance. We're not going to cover that section. Okay. Determining the sample size is the name of the section 7.5. So let's think back to an example that we've seen already, the one about the average length of stay of hospital patients. Remember, we created a 95% confidence interval for the length of stay. So just recalling this, this example that we've covered a couple times. Says, recall from section 1.5 that one way to collect relevant data for a study used to make inferences of population is a planned experiment. So this is going way back, right? There was a published study where you sit back and basically collect data, and then there's actually a planned experiment where the person actually has an active involvement. Perhaps the most important design decision faced by the analyst is to determine the size of the sample. That's really very important. If we want to know what the average miles per gallon is for people that drive around in Portales, or if we want to know what's the average amount of miles driven for the average resident each day. So what we want to, really one of the most important questions is, well, do I ask 10 drivers? Do I ask 100 drivers? Do I ask 1,000 drivers? Or some number in between those 3 values. So determining how many we actually need to get reliable data. That's what this section deals with. All right? So thinking back to example 7.1, in which we estimated the mean length of stay for patients in a large hospital. They sampled 100 patients which made it easy to find the square root of n, right? Because then that was just 10. And then we created a 95% confidence interval by doing x bar plus or minus 1.96 times the standard deviation, right? So that's a review of what we did basically all last week. Now this piece on the right, this is the amount of distance we go above the mean and below the mean, right? So in the middle is x bar. To the right is plus 1.96 times the standard deviation. To the left is 1.96 times the standard deviation subtracted. Now there's going to be a specific name for that distance that we go on either side of the sample mean. All right, what if I want to make that distance on either side of the sample mean as small as possible? Right, I want a small margin of error, we'll call it. All right, and even in those political things I pulled up last week, it would show a plus minus 5% right in the bottom of the window, and it would say that's the margin of error. That's basically what it is in a confidence interval. That 0.78 is the amount of error that we have above and below the mean. Now what if I want to make this as small as possible? The way that I make the margin of error smaller is by increasing my sample size. All right? So consequently, our estimate x bar was within 0.78 days of the true mean. And it says day because it's less than 1 day. Mean length of stay mu for all the hospital's patients at the 95% confidence level. That is, the 95% confidence interval for mu was, so this is the whole distance, right? 1.56 was from the low end to the high end. So that was the range of our confidence interval. Does everybody kind of see what's going on here, how they're talking about it? So in general, we could say, so here's x bar. So that's some distance here. So this distance here is 1.96 times sigma of x bar, and this is subtracted 1.96 times sigma of x bar. All right, does everybody agree with that? That's this distance here, and then that's this distance here. So the entire range from here to here is what they're talking about here. The confidence interval was mu. So the interval itself was 1.56 days wide. Right? It was 0.78 over here and 0.78 over here. Now how do we shorten this, right? How do we shorten our margin of error? I want to make this as close to x bar as I can get. Or get to, as close to x bar as humanly possible. All right? We can never actually equal it. So here's an example of what happens. So here's my confidence interval for n equals 100. So this distance was 0.78, so I basically drawn the same type of picture over here in general. But here, what if I push my sample size all the way out to 983 patients? And what they found here was the range of my confidence interval is 0.25 plus 0.25. It's only 0.5 as opposed to 1.576. So this confidence interval is 3 times smaller. Right? Does everybody see that? Because it's only 0.5 wide, where this one is 1.56 wide. And how do I come up with this value? Well, what I do is I set, how much do I want my error to be? How close do I want to be to the value? Once I set that, then I plug it just into my margin of error formula and solve for n. All right, so that's all we're going to do here. And we'll call this SE, or the sample error. That's the amount of standard deviations we go above the mean and below the mean. Okay, so we'll have a specific name for that called the sample error. Another way to think about it is the margin of error. Okay. Now suppose we want to estimate mu to within 0.25 days with a 95% confidence interval. So we're still creating a 95% confidence interval, but I want to shorten it. I want to make it smaller. So how many n's do I need? How many samples do I need before I can really make my 95% confidence interval smaller? That is, we want to narrow the width of the confidence interval from 1.56 days to 0.5 days, basically cutting it down to a third, as shown in figure 7.14b, which is what we've seen on the other side. How much will the sample size have to be increased to accomplish this? If we want the estimator x bar to be within 0.25 days of mu, then we must have, so basically I'm just going to set my 1.96 times my sample standard deviation. Notice how that's just one of the sides. So our sample error is how much we go in both directions, right? So we go 0.25 to the right, 0.25 to the left. That's not the range of the confidence interval. That's just half of it, okay? And that's why when you see it in like the political polling, it's always got a plus or minus because it's in both directions, either above or below. So we're going to call this our sample error, this 0.25. So what do? Well, they go ahead and just set the right-hand side of our confidence interval, right? Because our confidence interval looks like x bar plus or minus z alpha over 2 times sigma over square root of n. So they take the right-hand side of the confidence interval, they kind of ignore the x bar part, and they set it equal to 0.25. And then simply just solve for n. Now, of course, this would have to be given to you. Sigma would have to be given to you in the problem. If sigma is not given, we could always use S, our sample standard deviation. So all we do there is plug in 1.96, because that's our distance for a 95% confidence interval. Sigma was 4, and we want this all to be equal to 0.25. So let me set that up and kind of show how they solve for n. All right, I'll go through kind of a step-by-step process there. So all we're doing here is, here's our formula for the confidence interval. Alpha over 2 times sigma over square root of n. So what we're doing is we're taking this side right here, and we want it to be equal to 0.25. So that I go 0.25 above the sample mean and 0.25 below. So I'm going to take this right-hand side. I know z alpha over 2 for a 95% confidence interval is 1.96. So that implies I'm going to let 1.96 times, for this specific problem, sigma was 4, and that's given to you. It's not something you had to go find out. Divided by the square root of n. N is what we're solving for, and I want my error to be 0.25. Really, I could find this n value for any sample error. I could plug in just about any number right here. But the smaller this number is, the bigger n gets, right? The closer we pinpoint the actual mean, the bigger n gets. So how do I solve that equation? What should I do? First step. What do you guys think? I need to get n all by itself. I need to do a bunch of operations so that I get n equals something. That's what I want to get to, right? That's solving it. So I have square root of n in the denominator here. And how do we get rid of stuff in the denominator? Multiply both sides by it, right? Because if we had 1/2 x equals 2, I would multiply both sides by 2 to get rid of the thing in the denominator. So here I'm just going to multiply both sides by the square root of n. Now, something I'll mention, square roots cannot be negative, right? You can't take the square root of negative 25. So n is always going to be a positive number, right? Because that's always our sample size. So we don't have to worry about that type of stuff. But that's just something to keep in mind. Because you can't take the square root of a negative, but n will definitely be a positive number. And it won't be 0 either, because our sample size can't be 0. That doesn't make sense. So what I'm going to do here is multiply both sides by the square root of n, which I'm allowed to do to an equal sign, right? As long as I do the same thing on both sides. So over here I have square root of n over square root of n, which is just 1. So it implies now I have 1.96 times 4 equals 0.25 times the square root of n. Then what do I do to solve for square root of n? You don't want to square it yet. You want to get the square root all by itself first. So what do I do now? Not subtract, because what's the operation going on right here? Is it being added? No, it's being multiplied, right? 0.25 is being multiplied by square root of n, so we need to do the opposite of multiplication and divide. Just like right here, it's being divided, so we do the opposite operation of multiplication. So that implies, and I'm going to go ahead and write the square root of n on the left-hand side, equals 1.96 times 4 over 0.25, which is where they get to this point right here. Square root of n equals 1.96 times 4 divided by 0.25. And our book shows that it's equal to 31.36. That's not n, that is the square root of n. So I get to the point where I have the square root of n is equal to 31.36. And now what do I do? How do I get rid of the square root? Square both sides. All right. The square root of n squared is simply n, and I can find out what 31.36 squared is. Now what does n represent in this? Sample size. That's the number of people, right? So can n really be a decimal? Does it make sense for n to be a decimal? No. So what you do with these is you always round up. Whether it's correct or not, oh, this says 983, but in your homework, I think they want you to round up all the time. Even though this is 0.45, because all we're doing here is getting a sample size to create this sample error. So, I mean, adding another person will never hurt. Right? You'd rather have more data than not enough. But they went ahead and just said 983 right here in the book. But I was looking at your homework, and it said to always round up. So we take this n squared, we get 983.45, or n is approximately 983, and I would accept 984 on a test, either 983 or 984. The book went ahead and just said 983, so we'll go with that. So this is how big our sample needs to be if we want to make our sample error only 0.25, right? So that means we go 0.25 above the mean and 0.25 below the mean. So let's read what it says right here. Consequently, over 983 patients' records. That's a heck of a lot more than 100. Right? But you see why this is important? Because the hospital doesn't have to go and sample 9,000 people, which would take a lot more time and cost a lot more money. They know exactly how many people they need to sample to achieve the confidence that they want. And this is really how the real world works. All right? It's not really where they say, well, let's just go and take a sample and plug it into a formula and see what we get. It's actually the other way around. It's where, well, how good does it have to be? And then you work backwards and say, well, I need this many samples for it to be that good. Right? That's really how it works in medicine or anything, right? They don't say, well, we'll give you a drug and see what happens. They say, well, this is all that we want to happen, so how much of the drug do we need to give you? That's kind of how it works, all right? In general, we express the reliability associated with the confidence interval for the population mean mu by specifying the sampling error within which we want to estimate mu with 100 times 1 minus alpha % confidence. Right, so alpha is what's in the tails, in each tail. The sampling error, which I'll call SE. On your homework, it'll be called the capital S, capital E. So the sample error is this piece of the confidence interval, right? It's the thing that we add and subtract. So this is the sampling error. Right there. Which makes sense because it's got this little plus minus in front of it. Margin of error is the same type of thing. You can think about it that way as well. Is then equal to the half width of the confidence interval. Right? Because the sampling error is what we go above the mean and then what we go below the mean. So it's half the width of the interval. The procedure for finding the sample size necessary to estimate mu within a specific sampling error is given in the following box. Note that if sigma is unknown, which usually happens, we will need to estimate the value of sigma, which we could just go ahead and use S, our sample standard deviation. So here we go. Here it is. Determination of sample size for 100 times 1 minus alpha % confidence interval. So first it defines sample error. which is basically what I have written right here. SE is equal to Z alpha over 2 times sigma over square root of n. And then what it has down here is this exact same formula, but with it solved for n. In general, that's all it is. Because isn't it just squaring Z alpha over 2? Isn't that exactly what we do right here? Because we square both sides, so if I square both sides, I have to square that, I have to square that, and I have to square that. Because this is my Z alpha over 2, this was my sigma squared, and this is my 0.25 squared, my sample error. Now we went ahead and just found the quotient and then squared the quotient, which is the same thing. And so what that means is 4 squared times 4 squared is equal to 16 squared. Right? As long as we're multiplying everything. So all this second equation is solving that for n. So go ahead and write both of those down. So really on your homework, you'll be given all those values and you basically plug them into the formula. So SE, sample error, is equal to my confidence coefficient times the population standard deviation divided by the square root of the sample size. If I wanted to solve this for n after a lot of work, you get to the point where n equals Z alpha over 2 squared, so my confidence coefficient squared, times sigma squared over SE squared. So this is in general. We did a specific example beforehand. Did everybody kind of see what's going on there, why it's all squared? See, what another way this could have been written is all of this stuff in parentheses and then just with the square outside of it. That's the exact same thing. So this is equivalent to, so n equals Z alpha over 2 times sigma over SE with the entire quantity squared. It's the same thing. Because I could go ahead and apply this squared term in because nothing's being added or subtracted. It's all being multiplied. If this was Z alpha over 2 plus sigma, we couldn't do it that way. All right, it'd be a lot different. Because then you'd have what's called a binomial, thinking back to algebra. So does everybody see that this and this are the same, even though they kind of look different? And that's not a 6, that's sigma. There we go. For me, I think it's easier to do it this way, but they're equivalent. They're the same thing, right? Whether I square each thing and then multiply them together and divide, or whether I multiply and divide and then square, it doesn't matter. Okay? The value of sigma is usually unknown. It can be estimated by the standard deviation S from a previous sample. So if you're not given sigma, you'll be given S. Just go ahead and plug S in place of sigma. All right? The sample standard deviation. Another way could be sigma is approximately R over 4. But we don't really mess with that. Remember, that's an old approximation for the standard deviation, the range divided by 4, which is basically breaking it up into quartiles, right, into 4 quarters. All right, so let's go look at another example. So all we're doing here is simply finding our confidence interval and solving for n. Right? Or our sample error. We're not finding the entire confidence interval, but we're using the formula to find the confidence interval to find n. Now this is a funny problem right here. This book was written a while ago, so this doesn't have any, it doesn't know what actually happened, but it's actually talking about inflated footballs. Right? So we all know from the Super Bowl, right, what had happened. So this really proves Tom Brady knew something was up. Because look at the range. This is all footballs are supposed to range between, and he was like down in the 10-pound range. So that's how they knew something was up, because the football shouldn't have been that deflated. And another thing that happened, which is a little off subject, but not really, there was not one fumble at home the entire season. The probability of that happening was like 0.001. That wasn't supposed to happen. That can't happen. And it did. So that was another thing that went to say, well, the footballs probably didn't have enough air in them. But anyway, so let's look at this problem. Suppose the manufacturer of official NFL footballs, which I believe is Wilson, the company Wilson, uses a machine to inflate the new balls. So off the assembly line, they inflate every football to 13.5 pounds of pressure per square inch, right? That's what that deals with, PSI. When the machine is properly calibrated, the mean inflation pressure is 13.5, but uncontrollable factors like, humidity and elevation, a bunch of different things, influence the pressure so that the range is from 13.3 to 13.7 pounds. So notice the standard deviation would be 0.2 above and then 0.2 below, right? If our X bar is 13.5. For quality control purposes, the manufacturer wishes to estimate the mean inflation pressure to within 0.025 pounds of its true value with a 99% confidence interval. So right here gives me my SE, and from the 99% confidence interval, I know what my confidence coefficient should be, right? It's like 2.5 something. So that's stuff we've seen in the past. So here we go. Solution. We desire a 99% confidence interval that estimates mu at the sampling error. So they give you the sample error, 0.025. They give you a 99% confidence interval, so that means Z alpha over 2 would be Z of 0.005, which would be the value 2.575. So that's how many standard deviations we need to go above the mean to achieve 99% confidence, and below the mean as well. To estimate sigma, notice how sigma wasn't given to us here, so right here we can go ahead and use our R over 4 estimate. Because I do know what the range is. The range is the distance between our two endpoints, which is 0.4, and 0.4 over 4 is equal to 0.1. So our standard deviation will be 0.1. So there's the three values we need in the formula. Z alpha over 2 is 2.575. My standard deviation can be estimated as the range over 4, which is 0.1. And then our sample error is 0.025. So I want everybody to punch that in their calculator and make sure they come up with this value. And I'm going to do it both ways. So I'll do the multiplication and division and then square it, and then I'll square each term. Make sure we do this correctly. So it's 2.575 squared times 0.1 squared divided by 0.025 squared. Now I don't need to worry about parentheses here because I didn't violate any order of operations, right? Multiplication and division is on the same line. And it goes parentheses, exponents, multiplication, division, and subtraction. So multiplication, division, you just do it from left to right. So I go in here and hit enter, I should get 106.09. So now what I'm going to do is multiply them all together and then square. Let's do 2.575 times 0.1 divided by 0.025. And then I'm going to square that value. And we get the same thing. Look at that. So it doesn't matter if you multiply and divide and then square, or you square and then multiply and divide. It's the same thing.
Can you go over where you got the 0.1, the range again?
Sure. Let me go back to that previous box. And this is something we kind of messed with slightly. We talked about this way back, I think, in Chapter 3 when we were finding standard deviation of a sample. It was this thing right here. A conservative estimate for the standard deviation is R over 4. That's where that came from.
So you would take 13.7 minus 13.3 and just do 0.4 over 4?
Exactly, yes. The range of all the, so all the PSI of all the footballs range from 13.3 to 13.7. So that range is 0.4, which doesn't have anything to do with this confidence interval. That's different. Okay, that's the range of all the values. Then from the range, there's a conservative estimate formula, and notice how it just says approximately R over 4. So we only use that if we're not given sigma and we're not given S. That's our last kind of resort to come up with the standard deviation is R over 4.
Okay.
Does that make sense? That's kind of our last ditch effort to estimate the standard deviation. Really, in a perfect world, we don't want to use that. You know, we'd rather have all the sample points and actually create our variance formula and then find the standard deviation. But sometimes we have to use that. That's all the information we have. So let's get to the final answer. The final answer was 106.09. Now, what the heck does that number mean? That's the size of our sample. So that's how many footballs would need to be sampled in order to achieve 99% confidence of this mean inflation, or the average inflation. So 106.09, it says we round this up to 107, so there it is rounding up regardless of what the final decimal is. Because we're talking about how many things in a sample, we'd rather include one more than not have it. All right? It doesn't cost much more money to just sample one more football, right? Or one more patient. Realizing that sigma was approximated by R over 4, we might even advise that the sample size be specified as n equals 110. Maybe even make it a little bit higher to be more certain of attaining the objective of a 99% confidence interval with the sampling error of 0.025 pounds or less. To determine the value of the sampling error SE, look for the value that follows the keywords estimate mu to within. Because that's what our plus or minus of mu is, right? Because the sampling error was the right-hand side of our confidence interval. So we want to estimate x bar to within the sample error. Either so much above it and so much below. Okay? Sometimes the formula will lead to a solution that indicates a small sample size is sufficient to achieve the confidence interval goal. Unfortunately, the procedures and assumptions for small samples differ from those for large, as we discovered in section 7.3, which was the t-test, right? Therefore, if the formula yield a small sample size, one simple strategy is to select a sample size n equals 30. That basically means that's the smallest possible sample size. Right? You have to have at least 30 things before you have any idea of what the population is doing. You need 30 observations, right? A good way to think about that is, say, if you're a waiter in a restaurant. Before you can really determine whether you're in a restaurant that tips well or doesn't tip well, you would need to wait about 30 tables before you could really come up with a valid conclusion, right? Yeah, only waiting on 5 tables, you just don't have enough data to really know if the population of all the people that come to the restaurant are good tippers or not. Right? The method is easily outlined. The method before is easily applied to a population proportion P. So it's the same thing. We just let the right-hand side of our confidence interval, which remember was sigma of P hat, and P hat was found by the square root of P times Q over N. That's the stuff that's due tonight, right? Your homework that's due tonight deals with that. But the process is exactly the same. That's still your sample error, and then you just solve that for n. So you multiply both sides by z alpha over 2. The difference is your denominator won't be squared here. So watch, let's look what happens. I want to see, is there a perfect table for it? Or not your denominator, your PQ won't be squared because it's being square rooted. Everybody see that? What's going on there? So we'll look at a formula on the next page for it. So here's this, and then we'll look at a specific example. So we've done it for the confidence interval for mu. Here's the confidence interval for P. Notice how sample error is just equal to whatever was on the right-hand side of the plus minus. And then they just simply solve for n. So this is how you find your confidence interval for your population proportion. So they just take this and they solve it for n. All right, so my sample error is equal to z alpha over 2. And remember, for our population proportion, we only use z. It had to be greater than or equal to 30, right? Because of these two. Because n times p had to be greater than or equal to 15, and n times q had, the sample, had to be greater than or equal to 15. So the proportion stuff doesn't work for a sample size less than 30. So you don't use the t statistic when we're talking about population proportion. Because this has to happen, right? N times p hat has to be greater than or equal to 15, and n times q hat. That's one of our assumptions. So the sampling error is equal to z alpha over 2, whatever our confidence coefficient is, times the square root of pq divided by n. So what I need to do here is I'll divide both sides by z alpha over 2, or I can divide both sides by SE and multiply both sides by square root of n. So after some algebra, when we solve for n, which I'm not going to make you guys derive it, right? You're not going to have to show me how to solve for n, but you will have to use this formula. You have to be able to use this. So taking this one and solving for n, I get to z alpha over 2 times p times q. The z alpha over 2 is squared, the pq is not. Divided by SE squared. Does everybody see why this piece isn't being squared? It's because it was square rooted here. So when I square the square root, I just get back to PQ. Not PQ squared. So you'll be given all these values, right, in your question. Because the value of the product PQ is unknown, it can be estimated by the sample fraction of success as P hat from a previous sample. Remember that the value of P times Q is at its maximum when P equals 0.5, which means each thing are equally likely, right? Success is just as likely as failure, like flipping a coin, if success was heads. So you can obtain conservatively large values of n by approximating P by 0.5 or values close to 0.5. In any case, you should round the value of n obtained upward. So no matter what it is, round it up to ensure that the sample size will be sufficient. Because it's better, you're better off adding one more observation than taking away one. Right? So SE is the sample error. So it'll say estimate the population proportion to within blank. And that'll be your SE. All right? So let's look at this example. Cell phones. Here we go. A cellular telephone manufacturer that entered the post-regulation market quickly, right, because cell phones weren't nearly as regulated 10 years ago as they are now, has an initial problem with excessive customer complaints and consequent returns of cell phones for repair or replacement. Right? Their cell phones basically weren't up to snuff. Right? They weren't up to par with the rest of the cell phones, so people are complaining about them. The manufacturer wants to estimate the magnitude of the problem in order to design a quality control program. Right? How many cell phones are infected? Is it just a small amount, or is it a lot of their phones? How many cellular telephones should be sampled and checked in order to estimate the fraction defective P to within 0.01 with 90% confidence? Right? Okay. So we have our, just from this, we have our SE, and we can find our Z alpha over 2 from 90%, right? But we haven't figured out PQ yet. That's something we're going to have to do a little more investigating. So I know this value, and I know this value just from the question. Right? They were given to me. So let me go ahead and plug them in. So what is Z alpha over 2 for a 90% confidence interval? You guys remember? It was listed on that one box. 1.645. That sounds about right. Let me double check. Not that I don't believe you, Gary. I just want to double check. Yeah, right? No, that's it. 304. Let's look at it one more time. Just to remind everybody, because these are, you've noticed that these things show up a lot. And there it is. So for 90% confidence interval, here's exactly right. It's 1.645. Bless you. So that's going to be the value I put in for my confidence coefficient. 1.645. So I'm going to let Z alpha over 2 be 1.645 squared, right? Because that was the formula. Divided by, what was my sample error for this problem? Right, 0.01. Yep. And here's the giveaway, the 2 within. Estimate 2 within means this is my SE. So down here is going to be 0.01 squared. But up here is P times Q. And I'm not sure exactly what P and Q are at this point. My probability of success, my probability of failure, which are going to be complements of each other. Let's read exactly what the book says. In order to estimate P to within 0.01 of its true value, we set the half-width of the confidence interval equal to SE equals 0.01. The equation for the sample size n requires an estimate of the product P times Q. Right? We didn't have this. We could most conservatively estimate PQ to be 0.25, which is just failure and success are equally likely. So that's the most conservative estimate. P times Q, 0.25 is the biggest it could be. Because think if P was 0.6 and Q was 0.4, what's that product? What's 0.6 times 0.4? They're in a calculator. 0.24. So the highest this product can ever be is 0.25. So a good rule of thumb is to go ahead and make it as big as possible. Right? That's something that statisticians do. But this estimate may be too conservative. By contrast, a value of 0.1 corresponding to 10% defective will probably be conservatively large for this application. Now on your homework, you'll be given values for this. You won't just have to say, well, I'm going to go ahead and say it's 10%. That's just what's going on in this problem. Because if P is 0.1, what's Q going to be? 0.9. What's 0.1 times 0.9? 0.09, which is a lot smaller than this one, right? So that's still conservative. Not as conservative as defective and not defective being the same probability. Let's go ahead and let P be 0.1, so Q will be 0.9. Let's go ahead. So P, I'm going to erase P and let it be 0.1, and I'm going to erase Q and let it be 0.9. Then we'll see what would have happened if we'd have let it be 0.25. Therefore, the solution is, so when I plug all this stuff into the formula, does everybody come up with that number? Double check and make sure you put it in your calculator right. 1.645 squared times 0.1 times 0.9 divided by 0.01 squared. Enter. 2,435.4, but look, they round up. because you always want to round upward. If there's any fraction left over, you want to go ahead and round up, because we're talking about sample size here. So that means you need to sample 2,400 cell phones, which is a lot. But it's not a lot when you consider maybe there's 10 million out there, right? That's a very small proportion of 10 million. Thus, the manufacturer should sample 2,436 telephones in order to estimate the fraction defective P to within 0.01 with 90% confidence. Now, this 90% and us saying that the chances of it being not defective was 90% was just coincidence, all right? They have nothing to do with each other. Remember, this answer depends on our approximation of PQ, for which we use 0.09. If the fraction defective is closer to 0.05 than 0.1, we can use a smaller sample. It only takes 1286. What if I didn't know at all? What if I just let this be 0.25 or 0.5 times 0.5? Let's go ahead and do that in our calculator. So do 1.645 squared times 0.5 times 0.5 divided by 0.01 squared. So here's what would happen if I just went ahead and said the probability of it being defective was just as likely as the probability of it not being defective. So let's see what my sample size would be here. I'd need that to sample 6,000 cell phones, which, as you can tell, is a lot more conservative, right? I mean, the more you sample, the better your idea is going to be of how many are defective. But, I mean, this is 3 times as many cell phones you'd have to sample. That would take a lot more time and cost a lot more money. Really, in a perfect world, what you want is this number to be as small as possible to still get reliable results, right? That's what we're after with this stuff. I want to spend the least amount of time and the least amount of money to get the most reliable results. Okay? And sampling 6,000 cell phones is not the most reliable, but this would be my maximum sampling. Because no matter how I would change these two numbers, it would never be bigger than 6,765. Because if P went down a little bit and Q went up, that would actually make that number smaller, just like here, right? When P was 0.1 and Q was 0.9. Okay? And then here we go. Here's the word I've mentioned about 5 or 6 times. Cost. This is why we care about how many things we're sampling, because it costs money to do it. And really, it takes time, and time is worth more than money. Right? Nowadays. The cost of sampling will also play an important role in the final determination. Although more complex formulas can be derived to balance the reliability and cost, so it's basically how many do we need to sample so that it doesn't cost us too much, but we're still pretty reliable. Now that's a whole other section. That's Stat 313 and going further on in statistics. That's people that are in quality control for a certain manufacturer. That's the type of stuff they really care about. Right? How many things do I need to sample to be sure that such and such is going to happen? We will solve for the necessary sample size and note the sampling budget may be a limiting factor. Once the sample size N is determined, be sure to devise a sampling plan that will ensure that a representative sample is selected. What's the best way to do that? What word? To select a representative sample. Random. You have to select them at random. Right? So of those 2,000 cell phones we just came up with, you need to pick them at random. Right? They can't just be 2,400 cell phones in a row that come off the assembly line. Because maybe there was something that happened in that fraction of time that made them defective. So you have to sample them at random. And then here's a neat example about Medicare. Every section has this statistics and action stuff. And really, you kind of see this stuff in your homework a lot, right? Because I give you a lot of applications in your homework. This is talking about coding errors for Medicare, which happens, right? Okay. So that is determining the sample size. Basically, all it is it takes the right-hand side of our confidence interval stuff and solves it for N. That's all it is. Okay? which is really how statistics works in the real world. You say, well, I want to be this confident. How many things do I need to sample before I'm this such and such confident? All right? So that is the end of chapter 7. Let's just go look at a homework assignment, because I don't want to rush through chapter 8 for sure. Chapter 8 is the last thing we're covering. That's 7.5. Let's look at this one. Round up to the nearest observation. Notice it tells you on your homework. This isn't like rounding a regular value where if it's 0.5 you round below 0.5 you round down. For sampling you always round up, because you'd rather have more data than less data. So let's see if we can answer this question. If you wish to estimate a population mean with the sampling distribution error SE equal to 0.24 using a 95% confidence interval, and you know from prior sampling that the variance, notice how that's sigma squared, which is what's in our formula, so that's nice that it's got sigma squared, right? Is approximately equal to 6.3. How many observations would have to be included in your sample? So I'll give you guys a minute to try that one. So we're going to use the first formula we saw, right? Not the PQ formula. We're going to use this formula. N equals Z alpha over 2 squared times sigma squared divided by SE squared. And notice this value it gives us is the squared value of sigma. So I just would plug in 6.3. You guys see that? I know it's kind of hard to see. Let me go zoom it a little bit more. There's all the pieces that you need. And it's 95%, so we know what Z value that is. What do you guys get? 421, that's it. Because it was 420.175, so you always round up. Now the thing to notice in this problem is make sure you don't square 6.3. 6.3 is already the squared value. Right? Because it says right here, the variance, it's known from prior sampling that sigma squared is 6.3. So you want to make sure that you don't square 6.3. So your answer is 421. And there it is. Well done. Not too bad with this stuff. All right? All the values will be given to you. You just basically plug them in and round up. Okay? And same thing. So here's our within confidence level of 90%. That's going to be, what was it, 1.645 was our confidence coefficient there. SE is 0.15. And here it gives you a range of values. So what do I do there to find my sigma?
40 minus 32 divided by 4.
Exactly. The range, which is 8 over 4, which would be 2. Right, because 40 minus 32 is 8 divided by 4.
SE would be 0.15.
SE would be 0.15, yep. Yeah, anytime you see this, population mean to within, there's the giveaway, the to within. Right? Okay. This one's got a second part to it.
On that one?
Yeah.
When you find the range, would you just use 32 or would you use 32 squared?
Well, it was 32 minus 40. It was 8. See, and I just clicked it and it changed the values again. So you're saying for the standard deviation?
Yes.
Okay, let's snip it out and look at it. You would use the range over 4. Because see how here it says, assume that the range of the observations will be equal to 4 times the standard deviation, which is the same thing. If R is equal to 4 over sigma, right? Because if R equals 4 times sigma, then that implies that sigma is equal to R over 4, right? When I divide both sides by 4. Because it says right here at the end, assume that the range of the observations will equal 4 sigma. Yeah, so to find the standard deviation, it would just be the range, which in this case is 8, over 4, so it would be 2. So sigma would be 2. And then square it, which would be 4. Yeah. And then on the other question, it says, assume it'll be 6 sigma, which all you do there, instead of it being R over 4, you do R over 6. All right? Which happens right here. Watch when I show the completed problem. See right here it says, calculate the approximate sample size, making the less conservative assumption that the range of the observations is equal to 6 sigma. So if R equals 6 sigma, then if I solve that for sigma, I divide both sides by 6, and I get sigma equals R over 6. So you just would change sigma. Yeah, that's a sigma, not an R, lowercase r. So that's what I want you to do in those two problems. Okay? All right. So this is due tomorrow by midnight. Okay? So right here. So 7.5. Section 7.5 is due right there. 7.14, which is tomorrow by midnight. Let's see how far we get in 8.1, because I have it assigned to be due tomorrow by midnight. There's kind of a lot of material in it, so we'll see how far we get. But really, as long as we lay the groundwork to 8.1 pretty solidly, the rest of the chapter will go pretty quick. Right? Because this deals with the hypothesis testing, the 7-step process. So it's a little bit dense, this first section. All right? Let's go look at it. Chapter 8, the last chapter we're going to do. Okay. Go back one page to the... So here's the intro page. Here's where it starts. Inferences based on a single sample. So now we're actually going to test. We're going to come up with some hypothesis. We're going to say, well, we assume this is going to happen. And then we'll say, well, if that doesn't happen, then this will happen, which we'll call the alternative hypothesis. And then we'll test it. We'll say, is it true or not? Okay? So we'll go through, what, there's 6 more sections to cover. But a lot of them, like 8.2 and 8.3, we put together. Right? So it's once we lay the groundwork for the elements, the rest of the stuff follows pretty clearly. Right? It just goes and uses different tests. The Z statistic, the T statistic, right, like we've seen. So, where we've been, we've used sample information to provide a point estimate for a population parameter, which was like X bar, right? We created a sample, we found the mean of the sample, we call that a point estimator for the population mean, for the population parameter. Use the sampling distribution of a statistic to assess the reliability, which is called a confidence interval. So we create a confidence interval around our point estimator. What we're going to do in this chapter, introduce the concepts of a test of hypothesis. Right? Provide a measure of reliability for our hypothesis test, and then test a specific parameter, which is usually going to be the mean or the proportion. We're not going to deal with testing the variance. Heck, we didn't even do a confidence level variance from chapter 7, or a confidence interval for the variance. We only did confidence intervals for the mean and for the proportion, right? We didn't do it for the variance. Okay? There's an example about estimating the number of tissues in a box of Kleenex. I don't know if any of you have ever thought about that, but this definitely isn't tissue season, so it's a little bit different right now. It's not like the winter. Suppose you wanted to determine the mean level of a driver's blood alcohol exceeds the legal limit after 2 drinks. So determine whether the mean level of a driver's BAC exceeds the legal limit after 2 drinks. Or whether the majority of registered voters approve of the president's performance. This is questions we've asked before. But now we're actually testing it. In both cases, you are interested in making an inference about how the value of a parameter relates to a specific numerical value. Is it less than, greater than, or equal to? This type of inference is called a test of hypothesis and is the subject of this chapter. This is why we've had to learn about what the mean is and what the variance is and what the population proportion and all these different things we've built up to is so that we can get to the test of hypothesis, all right? Because we're going to use all those values as we're testing it. And it's not nearly as complex as it might seem, all right? It's really a step-by-step process that's somewhat tedious, but none of the steps are that difficult in their own right, all right? It's just a bunch of small steps. So we introduce the elements of a test hypothesis in 8.1 and 8.2. We then show how to conduct one for the population mean in 8.3, 8.4, and 8.5. And then in 8.6, we talk about the proportion, the binomial, success or failure, right? P and Q. And we don't do 8.7, all right? So what are the elements of a test of hypothesis? Suppose building specs in a certain city require that the average breaking strength of a sewer pipe should be more than 2,400 pounds per foot. I.e. per linear foot is what they call it in the right in that field, in the plumbing field. Now, of course, this makes sense that you want sewer pipes to be pretty strong because we don't want these things breaking. All right? Each manufacturer wants to sell pipe in that city must demonstrate that their product meets this specification. Note that we are interested in making an inference about the mean of a population, right? The average of all the sewer pipe. However, in this sample, we are less interested in estimating than we are in testing a hypothesis about its value. So we're not trying to estimate it. We're just going to say, is it equal to or is it less than? All right, and we'll kind of see this as we do these problems. That is, we want to decide whether the mean breaking strength of the pipe exceeds 2,400 pounds per linear foot. Right? If it exceeds it, then it will go into production. If it's less than it, then it won't. All right, so that's our 2 hypotheses. Is it greater than 2,400 or is it less than 2,400? A statistical hypothesis is a statement about the numerical value of a population parameter. And that parameter in this case would have been the mean, right? The mean breaking straight. Bless you. So a hypothesis is a statement about a parameter. We hypothesize. This happens in science classes, right? I'll hypothesize that when I feed a plant a certain amount of Miracle-Gro, it'll grow by 3 inches every day. That's a hypothesis. And the hypothesis is, I don't know how you exactly say that. The hypothesi? No, the hypotheses. So, as we go through these, this first section is really just identifying what the hypothesis is. We're not even really going into the actual testing of it yet, okay? So the first thing you do is set up a hypothesis. That's just like any experiment. What do we think is going to happen? The method to reach a decision is based on the rare concept explained in earlier chapters. So we'll really talk about this in real-world examples, right? So this is very abstract stuff that we're talking about here at the beginning, okay? So just stay with me. First, we define 2 hypotheses. The null hypothesis represents the status quo, which just kind of means how it's always been done, right? That's what status quo represents. We'll do it how it's always been done. To the party performing the sampling experiment, the hypothesis that will be accepted unless the data provide convincing evidence that it is false. The alternative hypothesis or research hypothesis, which we'll talk about the definitions a little more clearly here in a minute, is that which will be accepted only if the data provide convincing evidence of its truth, of the alternative hypothesis's truth. All right? From the point of view of the city conducting the tests, the null hypothesis is that the manufacturer does not meet specifications unless the tests provide convincing evidence otherwise. So we're just going to go ahead and assume it doesn't make it unless the tests show that it does. All right? So this is a lot like in a courtroom. You assume somebody's innocent until proven guilty. All right? The null and alternative hypothesis are therefore, the null would be that the mean is less than or equal to 2,400, i.e. they do not meet specifications, and the alternative would be they do meet. They're greater than 2,400. So this is a specific example of a null and alternative hypothesis. Notice the notation that's used. The H sub 0, which is pronounced H naught. H naught is the null hypothesis. HA is the alternative hypothesis. So at the beginning of all of these test of hypothesis procedures, this will be your first step. Identify the null and the alternative hypothesis. All right? And trust me, as we get through this stuff, it'll be easier and easier to identify. All right? Because I really could set this problem up the other way around. I could let my null be greater than, and my alternative would be less than. All right? And I would still either accept H naught or either reject H naught or fail to reject H naught. And we'll see exactly why my language is that way. The null hypothesis, denoted H naught, represents the hypothesis that will be accepted unless the data provide convincing evidence that it is false. Right? This usually represents the status quo or some claim about the population parameter that the researcher wants to test. The alternative hypothesis represents a hypothesis that will be accepted only if the null hypothesis is rejected. Really, the data has to provide convincing evidence of its truth. Right? Like being guilty. Right? When you're in a courtroom, you're not guilty or innocent. You're either guilty or not guilty, right? You're either, there's either convincing evidence that you are guilty or you're not guilty. You're not proven innocent. Does that make sense what's going on there? So we'll kind of see that throughout the section. I'll kind of harken back to that example. This usually represents the values of a population parameter for which the researcher wants to gather evidence to support. All right? So very abstract ideas here. How can the city decide when enough evidence exists to conclude that the manufacturer's pipe meets specifications? Because the hypothesis concerned the value of the population mean, it is reasonable to use the sample mean. The city will conclude that the pipe meets specifications only when the sample mean convincingly indicates that the population mean exceeds 2,400 pounds per linear foot. Basically what they'll do is they'll find the sample mean and construct a confidence interval and make sure that entire confidence interval lies above 2,400. That's kind of convincing evidence, all right? Convincing evidence in favor of the alternative would exist when the value x bar exceeds 2,400 by an amount that cannot be readily attributed to sampling variability, i.e. our entire confidence interval lies above it. All right? If part of our confidence interval includes 2,400, then we're not convinced. All right? That's kind of how this goes. Okay. How do we do that? To decide, we compute a test statistic, a numerical value computed from the sample. Most of the time, it's going to be the z value. So it's the same z that we've messed with. See why I was so, why I put so many z questions on the last test? Because we're going to use it over and over again. Right? When the null hypothesis contains more than one value of mu, as in this case, h naught mu is less than 2,400, right? So mu could assume a lot of different values, any value less than 2,400. We'll see later on where our null hypothesis would just be not equal. So it could be below or above, all right? And we'll see those. We use the value of mu closest to the value specified in the alternative hypothesis. The idea that if the hypothesis that mu equals 2,400 can be rejected in favor of mu greater than 2,400, then mu less than or equal to 2,400 can certainly be rejected. Right? If we show that it's greater than, then of course our assumption that it's less than or equal can definitely be rejected. So that just kind of proves how they're opposites of each other. Does everybody see kind of how the alternative and the null don't have anything in common? They are mutually exclusive. Because both of these things cannot happen at the same time. Right? Then you've got a failed experiment. So our null has to be some form of data, and our alternative has to be the opposite of it. All right? They can't have any overlap. Something cannot fall in both of those regions. Right? Do you guys agree with that? So that's important when you're setting this stuff up. There can't be any overlap where both things could be accepted. And then here's an example of going through the test statistic. But let's look at the definition of test statistic. The test statistic is a sample statistic computed from information provided in the sample. Most of the time, it'll be the z-test. We'll see some things where if our n is less than 30, then we'll have to use the t-test for our test statistic. All right? But most of the time, it's going to be the z-test. Is a sample statistic computed from information provided in the sample that the researcher uses to decide between the null and alternative hypothesis. And I know this is still very abstract. It seems like there's a lot of stuff going on in here. All right? So what we do is we set up our null and alternative hypothesis. Then we determine what type of test statistic we're going to use to test our null and alternative hypothesis. All right? If we're talking about the mean and our sample size is greater than 30, then we use the z-test. If we're talking about the mean and our sample size is less than 30, then we use the t-test. If we're talking about the population proportion, then we use the p-test, and we'll see that. Okay? So we haven't really talked about the p-test as of this point. If you examine figure 8.1, let me make sure we get to that if I want to look at it. Which is on the next page. So if you examine figure 8.1, you will note that the chance of observing X bar more than 1.645 standard deviations above 2400 is only 0.05. Right? Because that's our 90% confidence interval. So 5% lies above it, 5% lies below this 90% interval. In fact, if in fact the true mean is 2400, thus, if the sample mean is more than 1.645 standard deviations above 2400, either H naught is true, which what was H naught? What was the definition of it? Let's look at it right here. So H naught was defined as mu being less than 2400. The alternative was mu being greater than 2400. All right? So let's look what's going on here. So there's 2400. Here's our alpha. Alpha is 0.05 right here, right? So we reject H naught if this happens. Does everybody understand why we would reject it? Because H naught was defined as less than or equal to 2400. So if our test statistic fell up here, we would reject H naught and accept the alternative hypothesis. Okay? It's true and a relatively rare event has occurred. Or HA is true. And the population mean exceeds 2400. Because we would most likely reject the notion that a rare event has occurred, right? So we would say, well, it's either an anomaly or HA is true. We just go ahead and reject the fact that it's an anomaly. Okay? Just something that could happen. Just by the sheer fact of it being a sample, it is possible that we could get a population mean that's really high, but the chances of that happen are not very likely, so we just go ahead and accept the alternative hypothesis and kind of ignore this rare event happening. Okay? We would reject the null hypothesis and conclude that HA is true. What is the probability that this procedure will lead us to an incorrect decision? So this leads us to the fact of error, all right? Where we reject H naught when in fact it was true. Right? That's a bad thing that happens. And let me kind of write this up with a example of the courtroom, right? So let's just consider a small experiment. Well, I'm going to let my H naught, being the person, is guilty. Proven guilty, all right, by the court. And HA is not guilty. Notice I don't put innocent. I just put not guilty. All right? So here's our So let's say the person goes to court and then the person is actually guilty or the person is not guilty. So two of these things are good. Which two things are good? Well, that the person is guilty and we prove him guilty. Right? I mean, that's a good thing. That's what we want to happen. That's what the court system's supposed to do. Also, another good thing is that the person actually isn't guilty and he goes to trial and is proven not guilty. So those two things are good if those happen. That's where we accept H naught and H naught is true, or we accept HA and HA is true. These other two things are bad things, right? This is not what we want to happen. This right here, this box basically is the movie The Shawshank Redemption. Have you guys seen that? where he was proven guilty, but he was actually not guilty, just the fugitive, that's another one. Now that's bad for that person, but it's not necessarily bad for society, right? It really sucks for them. But all in all, it's not really going to harm anybody else, right? This right here, we call type 2 error. Right? And we'll call it beta. It's denoted by the symbol beta. That's the probability of type 2 error. Now this one's really bad, right? This is the worst one. It's when the person is actually guilty, but they go to court and get off. Right? So you're letting the criminal back out into society. That's type 1 error. Which we denote with the symbol alpha. Which is exactly what's going on here. So that's where we reject H naught and accept HA when in fact H naught was true. That's bad, right? When we go in and say, well, my alternative or my null hypothesis of them being guilty was proven false when in fact they were actually guilty. That's bad. Type 1 error is the one we want to get rid of the most. Now, I don't really want to come up with examples of that because but I think we all know of one happened near about the mid-90s, right, of that situation. So, where it was obvious that the person was guilty and they still got off. Right, a lot of times this happens with police error, right, where they don't conduct the investigation correctly, and that's why the person actually gets off. So that's the two types of error. When we reject our null hypothesis and it's actually true, that's type 1 error. And when we accept H naught and it's false, that's type 2 error. So let's think about this type 1 and type 2 error, which I haven't even got to the definitions yet because I want you to think about kind of what it means. Let's look at it for this problem. So which would be a more serious assumption? Right? Which would be the harder of the two things to happen to the city? Would it be to, type 1 would be to reject H naught when it's actually true. So we say that the pipe is strong enough and it's actually not. Or would it be worse to say that the pipe's not strong enough when it actually is? Yeah, which one would be worse for the city?
Saying that it is.
And it's not, right, exactly. Yeah, saying that it is strong enough, or it's not strong enough when it actually is, that just affects the manufacturer, right? That just affects the person selling the pipe. But when we actually put pipe in the ground that's not strong enough, that could have a drastic effect, right? That could cost the taxpayers millions of dollars if something breaks, and then the city's got to go in and fix it. So that would be type 1 error, is where we would say, yes, the pipe is strong enough, but it's actually not. Because we proved the alternative when, in fact, the null was true, all right? So we said it is strong enough when it actually wasn't. That's the worst of those two things to happen. Up here, the manufacturer is the only one that loses out. Right? Does that make sense, kind of what's going on? And in the other two cases, the pipe is strong enough and we say it's strong enough. The pipe's not strong enough and it's actually not strong enough. So those two things are fine. It's the two types of error that are a problem. And alpha is the probability of type 1 error, and what we'll call beta is the probability of type 2 error. So let's look at those two definitions. Type 1 error occurs if the researcher rejects null in favor of the alternative when in fact H naught is true, when the null is true. So type 1 is when we say the person is guilty. Oh no, that's when we say, yeah, the person isn't guilty in court when they actually were guilty. That's type 1 error. Because that's why you go to court in general. I mean, you don't go to court if there's no possibility of you being guilty, right? I mean, you got to go through all this stuff at the beginning where they make sure there's enough evidence and all that type of stuff. So the null hypothesis in any court procedure is that the person is guilty. But it has to be proven, right? You have to be proven guilty. If you're not proven guilty, well, then you're not guilty. But the worst thing is when you say they're not guilty when they actually were. So type 1 is when you reject the null when the null is true. The probability that it happens is alpha, and is actually shown by this region. Now, I haven't even talked about our test statistic falling up here. We haven't talked about the procedure for actually testing it. We're just talking about errors. What does happen after we test it? All right, so what if I went and found the mean of all these different pipes was actually 2,900? Right, was the mean PSI breaking point. Is 2,900 up here or is it down here? Well, we have to plug some stuff in to our Z statistic, right, to find out exactly where that value is, which you haven't got to yet. So, let's go back and look. So in this case, alpha would be 0.05. So our H naught would be the mu, the average breaking point of the pipe is less than 2,400. So our alternative would be the opposite of that. The average breaking point is greater than 2,400. We're going to use the Z test because our sample size was going to be big, which I don't think it explicitly said how many we're going to test. But we'll go ahead and just assume that it's big, so we're going to use the Z test. And our rejection region, the value where we reject the null hypothesis is if Z is greater than 1.645. If it falls within our rejection region. And this 1.645 number comes from our 90% confidence interval, right? And that type of thing will be given to you. What this number will need to be will be something that's given to you in the problem. Okay? Really, the trick or the stuff we're going to learn with this section is knowing how to set up all our null and alternative hypothesis. We're going to set those up correctly. Because if you don't set that up correctly, then anything you do after that, you're just wasting time, right? You've got to have your null and alternatives set up correctly. Note the rejection region refers to the values of the test statistic for which we will reject H naught. In our courtroom case, rejecting H naught means we're going to go ahead and say that the person's not guilty and accept HA. All right? So, in a courtroom, to reject the null hypothesis, just one juror has to say that they're not proven beyond a reasonable doubt. Right? It has to be every single juror on the jury has to say the person is guilty for them to be guilty. It has to be proven beyond a reasonable doubt. If there's one juror that's not convinced, then it's a hung jury and they can go back to trial, right? Or do a lot of different things from that point. But the worst part is when there's a hung jury and the person's actually guilty, right? Okay. To illustrate use of this test, so here's where they give you the data. We test 50 sections of sewer pipe. So that's your N. Is that a large enough sample to use the Z statistic? 50? Yes. Yes, it is. It's good. And then it goes ahead and tells us that X bar is 2460 and S is 200. S came from the sample standard deviation. So this data will be given to you in your tests, right? In your homework assignments. All right. So the test statistic, so they go ahead and find it here. So the mean was 2,400, right? That's the value that we're testing in our null hypothesis. Our X bar from our sample was found to be 2460. Now, is 2460 1.645 standard deviations above the mean? Well, we plug it into our z-scores, right? X bar minus mu divided by sigma divided by square root of n. All right, that's our z-test that we've seen. All right, that's our population standard, or our sample standard deviation, which was shown to be S over square root of n. They go through it and they get z to be 2.12. Does that value fall in our rejection region? Remember, where was our rejection region for this question? 1 point, right here. But if we get a z value that's in greater than 1.645, then we reject H naught and accept HA, right? So since z is 2.12, that value lies in the rejection region. So here's the rejection region. We found z to be 2.12. So I would reject H naught. I would reject the mean being less than 2,400 and accept the mean being greater than 2,400. So basically I'm saying the pipe is strong enough right here. Everybody see that? What's going on? Therefore, the sample mean lies 2.12 sample standard deviations above the hypothesized value of 2,400 as shown in figure 8.2. Because this value of z exceeds 1.645, it falls into the rejection region. That is, we reject the null hypothesis that mu equals 2,400 and conclude that mu is greater than 2,400. Thus, it appears that the company's pipe has a mean strength that is strong enough, right? So we can put the pipe in the ground. Now, what's bad is if this was actually error, right, and the pipe wasn't strong enough. That would be type 1 error. Okay? About 15 more minutes. Okay? So you'll notice none of the stats really behind this. The actual arithmetic behind it's pretty straightforward. There's not a whole lot going on. The hard part is setting up your null and alternative hypothesis. And then you're just plugging stuff into the formulas. Right? We're given these values, you plug them into the formulas, and you get a value back. Okay? So we're not really inferring or anything, right? We're just plugging and chugging here. We're plugging in the values that are given to us. How much faith can be placed in this conclusion? Right? Are we absolutely sure that those pipe are strong enough? What is the probability that our statistical test could lead us to reject the null hypothesis and conclude that the company's pipe meets the city specification when in fact the null hypothesis is true? So we reject H naught and accept HA when in fact H naught was true, which is type 1 error. Right? That is, we selected the level of risk alpha of making a type 1 error when we constructed the test. Thus, the chance is only 1 in 20 that our test would lead us to get to type 1 error. So we have a 1 in 20 chance, or about 5%. Now, that's too high for some applications. Right? If we're talking about airline mechanics and we're saying our engine will not fail, it'll fail 1 out of 20 times, that's not acceptable. Talking about the pipe here, that's a little bit different story. All right? So really, what's acceptable for alpha really depends on the specific example. Okay? What are we testing? Are people's lives in the balance or not? That makes sense. If people's lives are in the balance, we really want this alpha to be very, very small, right? For our chances of error to be very, very small. The test will lead us to conclude that so there's a 1 in 20 chance that we conclude that it does when in fact it does not. Now suppose the sample mean breaking strength for the 50 sections of sewer pipe was 2430. So we're changing it from 2460 to 2430. So we sampled 50 sections and we found that the mean breaking strength was 2430. Assuming the sample standard deviation is still 200, we get z to be 1.06. That definitely does not fall in our rejection region, right? That's less than 1.645. So since it doesn't fall in our rejection region, let's read exactly what happens here. Therefore, the sample mean x bar is only 1.06 standard deviations above the null hypothesized value of 2400. As shown in figure 3, this value does not fall into the rejection region. Right? Where is it? Oh, 8.3 is on the next page. So 1.06 would be about right here, right? Because this line is 1 standard deviation, so it would be about right there. So it definitely doesn't fall in the rejection region. Therefore, we know that we cannot reject H naught using alpha equals 0.05, even though the sample mean exceeds the city specification. This sample mean is still greater than 2400, but we still cannot accept H naught. Even though the sample mean exceeds the city specification of 2400 by 30 pounds per linear foot, it does not exceed the specification by enough to provide concrete evidence or convincing evidence that the population mean exceeds 2400. Even though our sample mean was this, that's not concrete enough to know that the entire population will exceed 2400. Because there only has to be one section of pipe that doesn't have the correct specification for it to break, right? And there's a lot of pipe in the city. And who knows how long these 50 sections are? And it doesn't say. Are they a foot long? Are they a mile long? You know, how big are they? And this is the type of stuff that really deals with, around this area, there's a lot of natural gas piping, right? South New Mexico, northern New Mexico. This is the type of stuff they're concerned with. Because if one of those pipes rupture, then we've got a big problem, right? Not just a stinky problem like this would be if a sewer pipe busted, right? Because then people's lives could be at risk. So here we go. It does not exceed the specification by enough to provide convincing evidence that the population mean exceeds 2400. So let's define type 2 error. Type 2 error occurs if the researcher accepts the null hypothesis when in fact H naught is false. So that's where it's really hard on the specific person. Right? When you say he's guilty when in fact he's not. So type 2 error is the Shawshank Redemption. That's a way to think about it. All right? Like the movie. You put away an innocent person. Right? The probability of committing a type 2 error is denoted by beta. This is called beta. It's got the little tail on the B. Right? So we call that beta. That's the probability of type 2 error. Now, of course, in a perfect world, we would want alpha and beta to be extremely small, right? We'd want the probability of type 1 error and the probability of type 2 error to be as small as possible so that they don't happen. Should we accept the null hypothesis H naught mu is less than 2400? So since our pipe length or our pipe strength didn't fall in the rejection region, does that mean we accept H naught? This is an interesting question. So it is possible to reject H naught, right? But you wouldn't necessarily reject H naught. Or accept H naught. Okay, you can reject it, but you don't really say we accept H naught. And conclude that the manufacturer's pipe does not meet specifications. So we are accepting the null hypothesis. To do so, we would be at risk of a type 2 error. All right, if we accepted H naught when in fact it wasn't true. All right? To do so, we would be at risk for type 2 error of concluding that the null hypothesis is true. It does not meet specifications when in fact it actually does. We denote the probability of committing a type 2 error by beta, and we show in section 8.7 that we're not going to get to, that beta is often difficult to determine precisely. rather than make a decision to accept H naught, where it does have a chance of type 2 error happening, we avoid the potential type 2 error by avoiding the conclusion that the null hypothesis is true. Instead, we simply state that the sample evidence is insufficient to reject H naught. So this is what happens. We either say H naught is false, or we say we don't know enough to say H naught is false. So we reject H naught, or we fail to reject H naught. We don't say we accept H naught. That kind of makes sense what's going on there? So it's kind of weird to talk about, but after you practice it a little bit, it makes sense. Because the null hypothesis is the status quo, the effect of not rejecting H naught is to maintain the status quo. In our pipe testing example, the effect of having insufficient evidence to reject the null hypothesis that the pipe does not exceed specifications is probably to prohibit the use of the manufacturer's pipe unless and until there is sufficient evidence that the pipe does meet specifications. That is, until the data indicate convincingly that the null hypothesis is false, we usually maintain the status quo implied by its truth. Now, you could probably read that 5 or 6 times and not exactly get what it's talking about. But this is what we get to. However, because we don't know the chance of type 2 error, right, what's the probability that the person is not guilty and we find them guilty? Rather than saying we accept H naught, we state that there is insufficient evidence to reject, or we fail to reject H naught. So we can either reject it or we fail to reject it. Okay? When the test statistic is not in the rejection region. So we can say it's not true, but we can't say that it is true. We can either say it's not true, or we can say we're not sure if it's not true. Those are our 2 conclusions we can come to. All right? Be careful not to accept H naught. When conducting a test of hypothesis, because the measure of reliability beta is equal to the probability of type 2 error is almost always unknown, if the test statistic does not fall in the rejection region, it is better to state the conclusion, we fail to reject H naught. There's insufficient evidence. We never say we accept H naught. And then this chart is basically the same thing I had drawn over there on the board. All right? So here they are. Here's the conclusions. So we either accept H naught or reject H naught. It is possible to accept the alternative hypothesis. You can't accept the null hypothesis. So we can accept H naught when in fact it's true. That's good. That's the correct decision. We can also reject H naught when in fact it's false, when HA is true. That's the correct decision. The other 2 is where we have error. Type 1 is the worst of the 2. Right? Type 1 means we set free a guilty person. We reject H naught when in fact it's true. And type 2 error is when we accept H naught when in fact HA is true. So since we don't know the probability of type 2 error, rather than say we accept H naught, we just say we fail to reject H naught. So H naught, so basically, whenever you get this case, whenever the test statistic does not fall in the rejection region, you basically have to do more testing. All right? We don't know if it's true or if it's false. We fail to reject. All right? So that's something we'll see a lot more as we get in this section. Now we have the next page. What do we have, like a minute left? So over here is our elements for a test of hypothesis. Now I'm not going to have time to get through all of these, but I think we've covered enough to where you can get in and try that homework and at least answer most of the questions. But we'll start class tomorrow right here talking about this elements of a test of hypothesis. Okay? First 2 things we do is we set up our H naught and our HA. What are we testing? What's the alternative? Then we determine what statistic we're going to use. It's either going to be Z, T, or our proportion testing. Then we determine what our region is where we reject H naught. We make assumptions, which will be different in every problem. Then we actually calculate our test statistic. And then we determine whether our test statistic falls in the rejection region or not. So it's a 7-step process. All right?